Greetings. This is Coly, and he will give us a talk about Linux I/O measurement in large-scale cloud services. You can start.
So, hello everyone. Coming here is the correct choice. So my talk, the topic is Linux I/O latency measurement in large-scale cloud service. Most of the content here is observation, analysis, and the challenge. I will spend more than half time to introduce the background, and for the less than half time to share the data we observed and a little bit analysis and some challenge we have to handle later. So my name is Coly Li. I worked for SUSE for almost 5 years in SUSE Labs. And after I left SUSE Labs, I joined the Alibaba Group to help them to build the kernel team in China. Currently, I'm the software engineer in Site Reliable Engineering team of Alibaba Group. The responsibility of this team just to maintain a lot of servers. A lot of means hundreds, thousands right now. Also, I'm the openSUSE user and developer. So first, I will introduce the hard disk failure in general. Just this kind of conditions that how the disk is broken. But most of the failures, the disk header crash or bad sector, connection failure or motor failure, or some other reasons that most of us, most of the reasons I don't know. For some fault phenomena, we can observe the I/O error complained from kernel, just from the D message. And we can find the hard disk just disappeared from the system. And maybe sometimes the whole system is frozen, and the kernel panic or data corrupted. But for cloud service, that might not be the major problem. For personal user, if the hard disk, there is a problem for the hard disk, maybe we just reboot the machine. If the machine works, we just back up the data. If the machine does not work, we just replace the hard disk and restore the data from backup. And just waste the time and money. For me, that's nothing very important. But for cloud service, if the cloud infrastructure serving millions users, the aftermath of hard disk failure is magnified to be much more complicated. In the next page, I will introduce what is the disk failure is magnified. A single disk driver failure may be magnified in cloud infrastructure because on a single node, there might be multiple virtual machine or container instance running on a single node. And a service request is not served on only one node. The request will be distributed on the cluster, and the result will be gathered and returned to the user. A different request on a single node, maybe many different requests are served on a single node. And time to time, maybe very frequently or emergent, there is a requirement that the program binary should be upgraded, maybe for bugs, maybe for version update, and a reason. And even we find the hardware is failure, we do not change them at once. Just schedule it to the decided time, maybe delay to weeks or 1 or 2 months, because some data center is far away from the company. maybe every 1 or 2 months, we just travel there to replace the hardware. So if a single hard disk failed, maybe we will find a positive influence on many virtual machines, many requests. Even we cannot fix the hardware failure very fast. So here is some data we observe online for the hard disk failure. Yeah. We can see that for hard disk running online for more than 3 years, the fault percentage is quite high. It's around 0.5%. The number seems very small to personal usage, but for cloud infrastructure, every server have 12 hard disks. And right now we have maybe 100,000 servers. That's a big number. Here is the fault rate among different hard disk vendor. I'm not authorized to show the name of the vendors, just name them A, B, C. Here's the fault rate among all vendors. I mean that all the failed disk from the whole IDC, and we just divide them against the vendor's brand. Yeah. And that picture is the fault rate just within each vendor. That how many hard disks we bought, and how many hard disks among this brand just we found failed. Yeah. From the data, we can find that hard disk is quite easy to be broken, even much easier than the usage in personal users. Because in the IDC there is a shake, the hot, noise, a lot of negative factors. So if disk failure results in kernel panic, we are lucky. We are lucky because there are a lot of copy or duplication among the infrastructure. Panic doesn't matter too much. All virtual machines or instances have to be migrated or restarted. And data has to be balanced or rebalanced to other nodes, and wait for a range time to repair or replace the hardware. That's okay. That's okay. Because there's no very tight relationship between each node in the cluster. If one node died, that's okay. We just transfer the service to other nodes, because we are not able to always fix the hardware at once. If the server downs, we always arrange a decided time, maybe delay 1 or 2 weeks at a site to replace them. But if disk failure results in long latency I/O, that's headache. Because a service request might be distributed among 100 servers. If 1 or 2 servers take too much time to return the result, the whole service request will be made very slow. And the program binary updates are blocked. That's because sometimes the hard disk is there. We can see that from the system. But when we try to access I/O on a device, the operation is blocked. For some daemon program, if they happen to access the I/O, the disk, and do the I/O and blocked, and the operation people want to update the program, the updated program will return a EBZ or something else that we cannot update the binary, just because the inode is busy. Because we have a lot of service, a lot of virtual machine or instance running on a single node. We have around 10 or 12 hard disks. Only one hard disk does not work. The rest can still provide the services. But if the system daemon is blocked and we are not able to update them, that's headache. That means the whole system, all the services running on this server is defunctional. That's why I say that negative influence of hard disk failure is very easy to be magnified in large-scale cloud service. Yeah. But how much I/O latency means a hard disk is almost broken? It's not easy to see, because fast and slow is relative to everyone, different person. But we need to know that if the latency of the I/O on a disk is too slow, we should not use this disk anymore, because the negative influence will be magnified to the whole cluster. We need to disable or isolate the hard disk at once. But how much latency is, it's not a simple story. Yeah. So let's see that where the I/O latency comes from. The major I/O latency observed from application comes from that the application being preempted by the processor scheduler, or the waiting for some available clearing pages. That means that maybe the buffer I/O and delete too much pages. There is no clean page, so waiting for the write back to reclaim more clean pages to continue the I/O. Or some locking bugs. Yeah. That's easy to encounter if we have a lot of machine. And the I/O request just insert into the I/O scheduler and needs to stay for some time to reorder. There is some delay. And the I/O issue to the hard disk, just waiting for the complete, that's kind of delay. Most of the I/O delay, I/O latency caused by almost a broken hard disk comes from the last two reasons. That's why that we only measure the I/O latency from the application is not enough. Because if we measure the I/O latency from application only, maybe we will counter this and this into the latency. But that's incorrect, because the first two reasons for the latency is not related directly to hard disk. Yeah. So the previous pages just introduced the background that why we measure the I/O latency, because very long latency introduce negative influence to our service, and the negative influence is magnified to the whole cluster maybe. So we just want to measure the I/O latency and learn that what threshold we could use to make the judgment that the hard disk is almost broken, and we should isolate the hard disk and replace them in a arranged time. Yeah. So right now, let's get to the meat part. So we do not only measure the latency from application level, also we need to measure the latency from kernel. And there are some motivation from this work. First, we need to identify the slow hard disk. Slow means the hard disk is almost broken, so the I/O is very slow. I don't mean that some healthy disk is just very slow. I don't mean this. and ignore all the latency that no relationship to the hard disk. For example, the locking or the write back, pause the process or the prompt. Ignore them. So we can learn I/O latency threshold from almost a broken disk. We learn the number and use this number back to the online system to check. First, if the number is correct. Second, we should detect the almost failure disk before it really very slow to make the service very slow. And after we find and identify the slow hard disk, that's easy. We just mask the hard disk from application, maybe from a name node, or maybe from some application just on each server, just a mark, do not access this hard disk anymore. That's all. And we maybe sometimes there are 3 or 4 hard disks on a single node, all failed. We just decided to shut down the machine and then replace hard disk. But there are some restriction because the whole system is online. They're really making money by serve other people's, just like change something on a running car. So from the operation team, they require that no kernel reboot. If there is kernel reboot, that means that the data has to be rebalanced. And the virtual machine or instance have to be migrated. That's a penalty on time, on traffic. So no kernel reboot. And no volume reboot or file system reformat. That means it's unacceptable if we just change some code in the kernel or in block layer. We have to ask the operation team to rebuild the logic volume or reformat the whole file system. That also means they have to maybe rebalance the data, reboot the system. For the rebalance the data, for a server with around 12 hard disks, and each hard disk is 2 terabytes, that spend a really very long time. Even among the high-speed network, that spend a very long time. For the cluster with maybe 10,000 servers, that's midnight. So that's the mayor. So the operation team will not accept to reformat or rebuild the volume. And when we measure the I/O latency in the cluster, we should make sure that there is no too much. There has to be little performance penalty when we measure the latency. And when we measure the latency, the method should be tunable and flexible. So we just implement a method we call DM latency. This method just patch a kernel model. We just patch the device mapper code. So we avoid the global change in block layer. And because we need to measure the latency, so we needed some resource for the time step. We use this one, K-time guide. K-time guide use a global timer resource, which needs a spin lock when accessing the memory source. So the spin lock is a global serial code path. That is not acceptable for high-speed storage media, for example, PCIe SSD. But we tested. For hard disk, that's okay. For hard disk, most of the hard disks right now, the I/O dips is around 31 maybe. For 12 hard disk, yeah, just 300s, no more than 400s I/O issued to the I/O block at the same time. So for every second, no more than 400 I/O conflicts with the spin lock. That's okay. That's not too much. And we just changed device mapper. And in this method, that means we don't need to reboot the kernel. We just insert the kernel model and use it. If we do not use it, we just remove the kernel model. That's okay. And there are a lot of target device modes in device mapper. One of the simplest is the linear map. We just do a linear map on the existing file system. Everything is done. We don't need to reformat the file system. We just mount the device mapper target and read the data, all the metadata or data just existing on the hard disk. Because the mapping table is just in memory. We don't need to change any data on the disk. So we avoid to rebuild the volume or reformat the file system. And this method is very simple. The patch just change 3 files, just 200, no more than 400 changes in the patches. Very simple. Just we are not able to observe any extra latency on disk I/O in this method. So I see that little extra delay. For hard disk, that's okay. But this method is introduced observed latency for high-speed PCIe SSD. Yeah, so we just use this for hard disk. So this is the basic idea of DM latency. Here is the mapped device we used to mount the file system. And here is the device mapper logic. Inside the logic, there is a map table. The map table just decides which I/O should be issued to which underlying target device. For us, in this case, we just set up a linear target device for each disk. So here, only one linear target device. This is very simple. So we don't need to do something like a mirror or read. No, just a linear device, linear target device. And in device mapper logic here, we change the code. 2 places. One is when I/O issue, we change the code start I/O account to write a timestamp in the structure DMIO. And when the I/O completed, and we change, we patched in the I/O account, just calculate the I/O latency and record it to mapped device. The mapped device is a per device data structure, so we can just record all different latency statistic information to each mapped device. And we just add a little change to the core data structure. For DMIO, add assign the long variable to record the time when the I/O is issued to underline. devices. And for this map devices, we add 3 data structure to record the latency distribution information. That's all. So that's why the patch is very simple. For the interface, when all the latency information record here, the kernel provides an interface to make the user space to access the latency data. That's the latency data in second level, millisecond or microsecond. And also there is a file to recite all the counters. That's very easy. All the information are text-based. So a bash, even a bash script can handle all the data. This is the format of the data exported. Easy. Just the range of the latency and the I/O numbers just hit the range.
Sorry. Can you help me interrupt? Just 1 second.
Can we get 2 minutes? Your time? Just 2 minutes, then we are going to go.
Oh my God.
An announcement to make. The bar is ready to take your orders.
So once the talk is finished, please go down, get some orders, and later on you should hopefully get some food. Okay. Thank you.
The helicopter will also be down there at the bar, so if you have questions, come down and join us.
Thank you very much.
Thank you.
Thank you very much. Okay, let's back to the topic. So this is all the information and the code running in kernel side. It's very simple. And all the advanced or complicated logic run in user space. Here is some real example for the data, how the data is used. In one of the online cloud system, we use a Ganglia monitoring system to monitor the resource or the performance number. My colleagues helped me to integrate the latency number into the Ganglia system. The different color, the line with different color means the different range of the latency. And the value means how many IOs just hit into the latency range. This system just integrated it maybe within 2 weeks. We still learn how to use it. Yeah. And another thing is, I want to mention is this method, there is no any resource allocation or reclaim. No. We just calculate the number and check the index and record the delay into the data structure. There is no tree walk on the tree or some memory allocate. No. So the patch is very simple. We don't need to worry about memory leaks or some very hot code path. No. So just I try to find 3 different typical cloud services to collect the data. One is MapReduce service. One is virtual machine cluster. And one is elastic block service, block storage service like cluster. Other services with a very high workload. So For some interesting phenomena are observed from the data we collected from the different services. When latency distribution it is displayed in the form of diagram. For the data, just the data in number, I don't have too much sense. But when we translate it into diagram, interesting. Sorry, it's not very clear. I will try to explain. There are some observation from the data. First is I/O latency in microseconds level. I don't find any regulation from the latency. I mean, from the data, I cannot recognize is it some kind of service or is the hard disk broken? No, no regulation. I guess maybe the reason is normally hard disk complete I/O around 10 milliseconds. For the latency within microseconds, I mean less than 1 millisecond. That's just a catch-to-catch copy. Because the model is not able to complete the I/O within so small time. So it's just a catch-to-catch memory, catch-to-catch memory copy. So there is no real disk platter access. Observation 2. Slow I/O disk are easy to be identified from other disks in the millisecond I/O latency. Here is the verified healthy disks. Verified means we check the disk whether it's really work correctly or healthy. For this disk, latency distribution like this. All the I/O latency hits here. It's just within 10 milliseconds. Yeah, this. And for the verified slow disk, the latency distribution like this. Here is around 500 milliseconds. They are very different. And we also observe some distribution that we call that suspicious. Like this, there is a long tail of the latency, long tail. But for the online monitoring system, there is no complaint that the disk I/O is very slow. I need to check because I feel maybe there's some bug for the online monitoring system. Or maybe we need to conclude some rules that we need to pay attention on this kind of latency distribution. So we can see that from the graphics, most of the I/O latency on really slow hard disk are much more beyond 10 milliseconds, even more than 300 milliseconds. The average number is around 500 milliseconds. Observation 3, the I/O latency on healthy disk, the distribution very similar to a chi-squared distribution. Doesn't matter. I just find the shape is very similar. No reason. I just think that it's like a chi-squared distribution. I don't know why it looks like this, but it's reasonable because for a healthy disk, most of the I/O latency should be here. The observation for this I/O latency distribution on slow disk looks following a likely normal distribution. Yeah. Like this, there is a peak and a decrease on both sides. I don't know why. I don't know why. Because right now from the data, I only find 3 very slow and verified very slow disk. So I need more data to make the more accurate conclusion. But at least we know that we can learn some data from the graphic. Maybe we can set some threshold to check whether the disk is very slow among this data. So after we learn from the real data, we have some conclusion. One is I/O latency distribution is independent from I/O patterns in real world. Because in theory, continuous I/O request should be much faster than a random I/O request. But from the above data, which is collected from different typical cloud services with different I/O patterns, there is no distinct difference on I/O latency distribution pattern. I mean, in the long term, there is no difference. In other words, no matter continuous, random, or mixed I/O patterns, with long time real workload, I/O latency distribution is similar on health hard disk. I mean, the distribution on all healthy hard disk, they looks very similar, no matter which kind of I/O patterns. The same rule works on a slow hard disk. Conclusion to this, it seems that 500 milliseconds and 85% might be a threshold value to decide whether a slow hard disk is about to fail. There is no any scientific reason. We just gather data from all the data we observed from the online systems. Because we are not only to use this single number to determine whether the hard disk is about to fail. We also need to know how many I/Os are slow I/O among all the I/O requests. And we observe that on real slow disk, on a real slow disk, the I/O request number just after here, it's around, if here is the 500 milliseconds, all the value after the point, this up to 85%. Yeah. And then there is a question. That the latency measured by DM latency is not exactly hard disk serving delay. Why? Because when the device mapper issued the I/O request to the underlying layer, we record the timestamp. And we calculate the latency when the I/O completed back to the device mapper layer. For the underlying layer, there is I/O queues for each underlying devices. And there is I/O elevator for each underlying devices. the request has to be stay in the I/O elevator to be reordered with a different I/O priority by the I/O scheduler. That takes time. Right now, the latency number returned by DM latency is the sum by two parts. One is the latency in device I/O queue. One is the latency in hard disk. So, in current observation, latency in device I/O queue influence little, very little on the I/O latency distribution. But it's only current observation on limited hard disk from limited servers. We need more time, more data to make decision whether it's real that the delay in the I/O queue has little influence. Yeah. Last one, the challenge. This is the challenge, and the next work I'm about to do. One is we need more accurate I/O latency measurement. Divided the current latency statistic info into two parts. It's better to know how much time spent on the I/O scheduler and how much time really spent on hard disk. Currently, we find that this information should be very helpful. And if we want to measure how much time spent in I/O scheduler or in hard disk, we need more data structure for time step. And when we record the time step, I have to try my best to avoid global lock. Global lock means the parallel I/O requests have to be serialized. That's the performance penalty, performance killer. So if I use the time step counter, the counter is per CPU. So in case that the CPU which the I/O completed back is different from the CPU which the I/O issued. So the latency calculated by different TSC number should be very inaccurate. If I use a global timer resource like HPAT or something like that, or use a K-time get, there is a spin lock inside, which means on the high-speed I/O devices, for example, PCIe SSD, hundreds or thousands of requests conflict on the spin lock. That's a big performance penalty. So how to solve this problem? That's the challenge. Another is kernel ABI compatibility. If the modification in the kernel, not the kernel model, sometimes the third part or the commercial driver reference this kind of in-kernel routines or data structures. If we patch these routines and data structures, this kind of driver should not work correctly. Maybe the system will crash. So that's a challenge. How to get the correct latency with the compatibility of the kernel ABI. That's hard, very hard. And we need more testing, more server, more service, and more workload. That's possible, because there are a lot of machines. Yeah. In the next several months, I will continue to work on this topic. Okay, credits.
Okay, then I have a suggestion. I don't think you need to measure all I/O requests. A representative sample should do. So he could write a version of k-time get that uses try log and can fail and ignore the failure cases.
Good. Good. Let me think. Good suggestion. Yeah. So, any question?
What is the data structure you use to hold all the data you collect? And,
Yeah.
Where do you keep them? Because that could be time consuming. Okay. I'd like to ask Good. I would like to ask, what is the data structure you hold all the information you collect? Is it, you said it is simple, but is it a file? Is it you collect it in a database afterwards? Because that could be time consuming
Yeah.
above.
Let me calculate. Let me explain. For every I/O inside the device map layer, there is this data structure DMIO. I added timestamp just here. So when the I/O completed back to the device map layer, I just call k-time guide the function to get another ticks. No. It's a microsecond. It's a microsecond, and I just minus the previous value by the current value. So there is a latency in microseconds. There's a judgment for the range if the latency within 1,000, it's 999 microseconds. Just record here. For here, I just do the mode calculation. Because every item in the array it's a 10 microsecond. So I just mode the value by 10. So I can get the index number, just increase 1. That's all. So that's very fast. There's all calculation, even there is a divide calculation, but all the calculation are integer based. And I just do a mode. That's fast. I mean, comparing to the hard disk I/O, that's very fast. Yeah. And when we display the data, only when we read the data from the file, we just display all the information from the data structure. So most of the time, I mean maybe every 5 seconds or every 5 minutes, this file is read once. So within the interval, just increase each item by 1. That's all the operation. So that's very fast. Please.
Okay. So you check only hard disk, or you check if you have, let's say, SSD in your system. You check if your SSD have some problem. This problem is happening also in SSDs.
For SSD, especially the high-speed SSD, that's a different story.